So here we are, 800 years on from King John declaring through the mechanism of the Magna Carta that he was going to be less autocratic in his dealings with his subjects. In fact, he was going to give them the rights they duly deserved. And things like this 800th anniversary of the Magna Carta we can predict, and we know that those events are coming. But there are other events in the unfolding of the world towards its final conclusion that we can't predict. And one of them was the dear little Philae lander on waking up yesterday morning, and apparently he was transmitting to the world, and no one was listening. And it was only a day later that someone bothered to listen and noticed that he'd been chatting away and saying, "Hello, world, how are you?" So I take all those things very personally, and very pleased to hear that news, because I was beginning to wonder whether I was just talking to myself, which we all know is what mad people do. So today I bought a bottle of Ardbeg's recently released Perpetuum, which has a little infinity symbol on it. I said that the Auchantishan was going to be the last of the non-age statement single malt Scotch whiskies that I'd be using in this series, but the Ardbeg Perpetuum has intervened, and the reason I couldn't help buying it was because of the infinity symbol and how it relates to fundamentally what is the ultimate constituent of this universe, of God, of you and I, of everything there is, and it all comes ultimately from nothingness. So it's about time we sort of had a look at how that works, and everyone's had a little bit of a glimpse of the idea that the world that we live in is some sort of computer simulation, and most people are familiar with the Matrix series of movies, but there have been many others that explore this idea of a virtual world in which there are simulated creatures, and that there is a computer above all that's actually hosting the whole operation. And although it makes for good Hollywood entertainment, most of us know how big the universe is, and we look out there and in reality we say, well, this is not happening. Obviously there is not a big IBM PC in the sky with God with a beard at the console typing away and you know, controlling how the world works. Well, I say obviously not. There's a little bit of that going on, but we'll have a look at how that might work. So the problem with having a computer that is simulating a simulated world, if we were to be living in a simulated world, is that you then have to ask, well, is the computer that's simulating this simulated world itself in a simulation? And one of the oldest paradoxes that we know of is that of self-reference, and in fact Paul mentions it in his letter to Titus, where he says all Cretans are liars, even one of their own said as much. So the implication being, of course, that that particular Cretan was lying about all Cretans being liars, and it's a self-referential paradox that one cannot escape. So if we look at modern computing, which is a field I work in, most of the computers that you connect to on the internet and resources that you connect to on the internet are actually what are known as virtual machines. This is where instead of the computer that you're familiar with, the hardware that you know, which is your laptop or your computer at home, which has power coming into it, and it has electronic circuitry in it, and on top of that is your operating system and your software, everyone's familiar with that, but not so many people are familiar with what we call virtual machines. And you can go and download one of these from Oracle. There's a thing called VirtualBox, and I entice you to go and download it. It's free, and you'll find that you can actually make a software equivalent of a hardware machine. So you've got your laptop, on it is running your operating system, which might be Windows, it might be Linux, and then you load VirtualBox and you can fire up what's called a virtual machine, and that virtual machine is virtual hardware. So it's the hardware, the electronics, the CPU, the memory, all of the hardware that you're familiar with that's actual hardware is actually being simulated in software by this software virtual machine. And it's an amazing thing because you can fire it up. It's got a BIOS, you can put in a CD, a virtual CD, you can load an operating system, you can load your programs on that virtual machine, and it behaves in all aspects like a real machine, except it's actually in software. And we all know that ultimately the virtual machine is actually running on, that's actually what's called a hypervisor. It's actually running on the host physical machine that is your computer. But imagine this for a moment, that you have a physical machine, you then have an operating system, and you have a virtual machine, and then within that virtual machine you then fire up the software that emulates another virtual machine. And so you have a nested reality, a bit like when you look in two mirrors, one behind you and one in front of you. If you just tilt the mirrors slightly, you'll see that infinite regress of images of yourself reflected back between the mirrors. And that's what we call a reductio ad absurdum, or infinite regress. And rather than that infinite regress, let's imagine that instead of having a physical machine, then a virtual machine, and virtual machines all the way down, which becomes very slow, that we actually have the first virtual machine simulating another virtual machine, and then that virtual machine actually ends up simulating the first virtual machine. So we have basically a self-referential loop, a bit like this infinity symbol, or a little bit more like a Möbius strip, where one virtual machine simulates the other, and the other virtual machine is actually the host for the first virtual machine. They both simulate each other. Okay, so the point about the real physical machine, that is your laptop that's running all these virtual machines, is that it's subject to what we call the laws of nature, the laws of physics. And we all know that you can't actually achieve a perpetual motion machine because friction, ultimately, and that's all part of thermodynamics and the laws of physics, say, for clear reasons that are understood, that the interactions amongst the atoms, molecules of any physical machine ultimately will generate heat and will cause any sort of perpetual motion machine to fail. But in the case of two virtual machines, each of which are simulating each other, there is no physical world. It's just a world of mathematics. It's just a world, in fact, of zeros and ones. So the only thing one has to have in order to start a universe that we exist in now, is to have nothing, or to have the concept of something, or the concept of one. Once you have zero, and once you have one, you have everything that you need to then start manipulating those zeros and ones into a computing machine, and into ultimately a virtual machine that simulates another virtual machine, and that virtual machine simulates the first virtual machine, so that, importantly, neither of them exists in any sense whatsoever, except when it is being simulated by the other machine. So we have traditionally always had a problem about creating something out of nothing. A lot of people, Laurie Krauss amongst them, Stephen Hawking has had a go at it. They talk about there being a quantum field that has perturbations in it, and that those movements bring into existence particles and the Big Bang. The problem is they have this quantum field in the first place. What we want to do is get away from the idea of the world being ultimately composed of mathematics, but to say that in fact computing is a more primitive starting point for a universe than mathematics, that in fact in the beginning was a computation, and it is that computation that allows something to come into existence which hasn't existed previously. So you have these two machines, each holding each other up by their bootstraps, and a couple of amazing things can happen with those machines. Firstly, they can simulate an atom of space. Now we know through joining relativity and quantum mechanics that the smallest area of space is 10 to the minus 43 meters. That's 1 divided by 1 with 43 zeros on it. It's a very small piece of space. But interestingly enough, it relates very closely to what we call the limiting speed of light. That is sort of the fastest propagational speed that anything can have in the universe when moving from point A to point B. So the first thing is that what we call a space atom, so that's this pair of virtual machines which are simulating each other, can simulate an atom of space, but they can also replicate. So you can basically have a machine in one cycle splits into 2, it splits into 4, it splits into 8. Anyone who's watched a fungus or a bacterium grow in a petri dish knows just how quickly that spreads. And so what we have is the potential for the inflationary, the violent and sudden expansion in the amount of space there is in the universe, and in fact the coming into existence of the universe in the first place. So when you have two virtual machines, you only have mathematics, you only have zeros and ones that are simulating each other. You don't have any space, you don't have any time, but as soon as they start replicating, and as soon as they start simulating an atom of space, you then have a universe into which other things start to get replicated by these two machines. By these space atoms, which increase in their number vastly and suddenly. When you have a space which is made of these virtual machines, instead of having a large computer that's then simulating the whole universe, you actually have the computer that's simulating the virtual machine that's in fact simulating itself at the most fundamental level of the universe, the space atom, this 10 to the minus 43 meter size dot of all the reality that we see around us. And the universe is very big. It has something like 10 to the power of 186 space atoms in the observable universe, which is about 100 billion light years across. So there are a lot of them, but they're finite in number, and they can keep on replicating ad infinitum. That is, they can just keep on making the universe bigger and bigger, but they're not infinite in number. They have a finite number. They can just keep on going, creating more and more of them. So the interesting thing about the two machines simulating each other is that they, in a sense, can create a time base. So if we imagine that this machine is on, and its job is to simulate this machine, and then this machine's job is to no longer be itself, but in fact to be the host to simulate this machine, and in fact they're just going, simulating each other, but there is actually a time base that is generated between those two machines simulating each other. And empirically, that is by performing experiments through general relativity and through quantum mechanics, we know that the ultimate, the smallest amount of time that can elapse in the universe is 10 to the minus 35 of a second. So that's 1 with 35 zeros over it, 1 over 1 with 35 zeros of a second. So there are 10, 1 with 35 zeros after it, that many periods in 1 second, which is long. But if we imagine the very small space atom, which is 10 to the minus 43, and this very small amount of time, 10 to the minus 35, it is in fact the propagation speed of light. So normally we think of light, excuse me, we normally think of propagation in the universe as being, well, you know, here you've got an object, and when it moves in the world, it's actually the same object moving across and going to its new location. But in what we call digital physics, which is where, you know, we sort of talk about a simulated universe in which effectively we think of the world as if space is static and full of these space atoms, and the space atoms don't move. They're like the squares in a game of battleships. But when we've got an object sitting at a particular point, each one of the parts of that object are defined within the space, the static solid space at that point, and that when we move, what's happening is that the information that describes, in this case, a glass, in those particular space atoms there, is actually transferred through input-output, I/O as we call it in the computing industry. They're actually moved from that point to an adjacent space atom, and a bit like when you see in Chinese or Korean displays of patterns in crowds where they all have, you know, a card that they hold up and turn, and the wave moves, a bit like a Mexican wave. Basically, this person says to the person next to them, right, you're going to take over the job of being a glass, and then the next one takes over the point there. And if we think that there's, in 1 meter, which is, there's a meter, that there are 10 to the 43 space atoms in that particular length, then the speed of light says that light, if we start from this point, light moves from that space atom to the next space atom. There are 10 followed by 43 zeros of these space atoms in a meter, but it moves from there to the next one, and it makes that movement in 10 to the minus 35 of a second. The reality is that it moves that 1 meter at the speed of light, if each one of those interactions as it goes along propagates along. And, you know, I showed the glass moving from there to there. It's very natural for us to think that here's my hand is actually the same hand that's moving from there to there, but in fact it's the information that is contained within that hand that is moving to a new location in space. So one of the great mysteries, and we'll go into greater detail about this, that prompted Albert Einstein to come up with his special theory of relativity was the fact that when light was shone with the momentum or the speed, velocity of the Earth going around the Sun behind it, it gave no further impetus, gave no further acceleration to the speed of light than shooting light sideways. And in fact, experiments have shown that shooting light backwards makes no difference. So this is counterintuitive. We think of a train speeding along in one direction. If we fire a bullet forward, in the forward direction of that train, it will get the speed of the bullet. If we were shooting that gun from a stationary position, added to the speed of the the train going along and sort of have a combined velocity of train plus stationary speed of bullet. And likewise, if we shoot the bullet backwards, it would actually lose some of the velocity according to subtracting relative to the ground on which the train's running, or what we call terra firma, that it would lose some speed. But in fact, what we see is that if we have a digital world, or a digital physical world, in which there is a solid foam of space-time atoms, that is, these self-simulated atoms which can simulate any part of the world. Ultimately they can simulate atoms and what we all know as air and solid stuff and fire and water, the Archimedean, Aristotelian principle elements, or elements as we know through mathematical modelling of reality. The fact is that these space atoms can simulate any of this reality, and they are static, and that if we were to shoot a photon from any object that's moving through that space, so let's say my hand was a light, as it goes, the moment that it shoots or releases the photon, it doesn't matter how fast it was going to the point at which it releases the photon. From the point it releases it, it then only travels at 1 10 to the minus 43 space atom every 10 to the minus 35 of a second. And it doesn't matter whether the light was going that way or that way, there's nothing you can do to make it go faster. Now, interestingly, as a result of special theory of relativity, physicists started actually accelerating macroscopic objects. By macroscopic we mean typically a proton or a alpha particle, or a neutron, but typically a proton, in an accelerator, so that it approaches close to the speed of light. And the problem that a photon encounters when it starts travelling at a speed approaching the speed of light relative to what we call absolute space, which is this solid foam, a bit like you know, that foam that florists put their flowers into, sort of green stuff. It's solid. I mean, it doesn't look solid, but it's actually immutable and absolute. Is that as you start moving that object through space, if we're just moving at non-relativistic speeds, the translation of the hand in that position through the space atoms to that position is trivial and very easy for it to calculate all of the reality of that hand there and recalculate it, all of the positions along that way. And you know, if I go at a certain speed, it still seems to manage to very effectively translate from there to there. But when you start accelerating protons close to the speed of light, you're actually running into a problem where the object is moving so quickly that it can't actually translate any faster, that you're actually running into like a sonic barrier, a bit like the sonic boom that an aircraft achieves, is that it's running into ever and ever increasingly the limit of the ability of the space-time foam, or the space atom matrix, to translate those, to translate that reality from one point to the other. So what I'd like to do is end now, give you some time to think about that, and in the next transmission from Philae, we'll see if we can talk about who else in the universe knows about this sort of technology. And I say that quite a few people, but one of the things I'm going to try and do is, it might be thought that I should have been a German philosopher. German philosophers were famous for people suspected being frightened that anyone might actually understand what they were saying. Their language and the way they talked was so obtuse. Kant, Hegel, Wittgenstein, they're all very much like that, and so I'm going to try and explain things in the most simple and accessible terms I can come up with. Anyway, thanks again for listening.